Alright, let's suppose we have a Noetherian module M. Let M be a Noetherian A module. This is probably a better way to say this. And let F be a surjective alinear map from M to M. Prove that's automatically an isomorphism. So that's a pretty strong statement, so let's prove it. Got a hint here. We'll do that. Okay, so F is surjective and alinear. We want to prove that's injective because that it's bijective, and it being alinear means that's a morphism, so then it's an isomorphism. Okay, for any natural number n, of course natural numbers don't include 0, f to the n is also surjective and also alinear because compositions of linear maps are linear, and obviously if you compose a surjective map with if you have a surjective map from M to M, then the image of f is going to be all of M, and so then the image of f squared, or the image of f composed with f, well, when you send all of M through f, you get all of M, and then when you send it through f again, you again get all of M, and so then composing it with itself any number of times, you're still going to get surjectivity. Alright, so we have this is surjective. So f to the n is surjective, and so let's see here. We know that the kernel of f to the n is a submodule of M. Do we need surjectivity in order to prove that's a submodule? I don't think so. All we need is that it's an alinear map. So I wouldn't say like therefore, because it's not. The fact that f to the n is surjective is not giving us the fact that this kernel is a submodule. The fact that it's alinear tells us that this is a submodule. So the kernel of f to the n is a submodule, and so now let's take an element x in the kernel of f to the n. Then if you send it through f one more time, so if you send it through fn plus 1 times, then this is the same as f composed with f to the n of x, and f to the n of x is 0 since x is in the kernel of f to the n, and so you're taking 0 and feeding it through f, and so you'll get 0 because it's a linear map. It's a linear map. It's an a linear map. Okay, so then this tells us that the kernel of f to the n is contained in the kernel of f to the n plus 1. Because if x is in the kernel of f to the n, then f to the n plus 1 of x is 0, so it's contained in the blah, 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 blah. Okay, so we have an ascending chain. The kernel of f is contained in the kernel of f squared, and we keep going. So by the ascending chain condition of which we get from Noetherianity, there is some natural number n, such that for any index greater than or equal to n, basically this chain stabilizes at n. Okay, so suppose x is in the kernel of f. We want to prove injectivity, so we want to prove that x is 0. Okay, f to the n is surjective onto m, so that means by surjectivity, we're using that, and so there's some element y in m such that if you the image under f to the n of y is precisely x. Then if you look at the image of f to the n plus 1 of y, this is f of x, which is 0. Okay, so f to the n plus 1 of y is 0, so then y is in the kernel of f to the capital N plus 1, but because capital N, this is where the ascending chain of submodules terminates, therefore f to the n plus 1 is equal to f to the n, so the kernel of f to the n plus 1 is equal to the kernel of f to the n. Okay, so y is in the kernel of f to the n, so then f to the n of y equals 0. And therefore x equals 0. Because, Yeah, because this is exactly x, because x equals f to the n of y, which we've just proven is 0, so x is 0. So every element of the kernel of f is 0, therefore the kernel of f is 0, and that's what it means, or that's equivalent to f being an injective map, and hence f is an isomorphism. And then we're done.